All right, so let's do 11.3 then. This is about the integral test. So I think I mentioned that the goal here is that we want to be checking to see if various sequences, or sorry, series will converge or not, and that we would be learning about several different tests that would help us to determine that. And so the first one we saw was called the divergence test, which is really just a test to see if a series diverged. It didn't really tell us anything about convergence. So if we want to talk about convergence, the first test that we're going to look at today is the integral test. And I'm not going to spend too much time on this one because this one is not really used much at all. So I'm just going to sort of quickly go through what the integral test is, and then we'll talk about the type of series that it's really the only thing it's good for is to show what a p-series is. And once we've established what a p-series is, we really don't really need the integral test anymore. But anyway, you can read about what it is and the reason that this test is not very often used. On the top of 11.3, you can see, suppose f is continuous, positive, decreasing, let an equal f of n. The series with those same terms an is convergent if and only if the improper integral is also convergent. So basically what we're doing here to check to see if a particular series is convergent, we're going to sort of compare it to an improper integral, or we're going to check what the corresponding improper integral actually does. And so take a look at that first example there. You can see here's a series, and the question is, does this thing converge or not? Remember, I've been saying the thing that we really care about for most series is just that question: does it converge or not? The question of what it actually converges to is not really that important, and often very difficult to find exactly what it converges to. But there are methods that you can approximate what it converges to very, very well, very closely. So that's really what people normally do with these types of things. Okay, so what this integral test does is it says we need to find a function that sort of matches the terms of this series for every integer value. So in other words, we want a function. This is kind of similar to that thing that we were talking about with finding limits of sequences. We just have to find a corresponding function that matches it for all values of x. And again, keeping in mind that the differences here is that this is a series, meaning that we only have, well, we have a bunch of terms added together here, and it's discrete values. In other words, the n is 1, and then it's 2 and 3 and 4, right, for the input values. But for the function, of course, we can put in any x that we want here, right? So this includes fractions and everything else. So what we want to do is just check, does this improper integral for this particular function, the one from 1 to infinity, for this function, does that improper integral converge or not? If the improper integral converges, then the series converges, okay? If the improper integral diverges, then the series diverges. You can kind of see why this particular test is not that great for us as far as like ease of use, really, in particular. It really requires that we check a lot of things, and the test itself is fairly involved as well. Like, what do we have to make sure of before we can even use this test? You can see right there at the top it says we have to make sure the function is continuous and positive and decreasing. All of that has to happen. And so even just checking that all those things happen, I mean, continuous is easy to check. Positive, somewhat easy to check. Decreasing, how do you check if a function is decreasing? Well, that requires like taking the derivative, right? And setting to 0, finding critical numbers, etc. I'm not going to bother with that on this problem. You can just take my word for it that that function is definitely decreasing for values of x that are bigger than 1 anyway. So we'll skip that. But in general, you'd probably want to check, is the function actually decreasing? Anyway, we'll assume that it is. So let's go ahead and do the improper integral. And so we have to remember how that works. We have to take the limit as b goes to infinity, integral from 1 to b of this integral here. Okay, so now we have to think back about how we do these, right? And so that's the first step on an improper integral, right? Change the problem bound, in this case infinity, to some letter, b, and then take the limit as b approaches that problem bound, okay? And so then this particular function, we can make a substitution, u equals x squared plus 1, du equals 2x dx, and you see that we already have the 2x dx here, so we don't have to divide or anything like that. They match exactly, so we just change that 2x dx into du, and then the x squared plus 1 becomes u, and so we get our new integral. Okay, now remember that these bounds also have to change. The lower bound is going to change to 2, the upper bound is going to change to b squared plus 1. Remember how you change the bounds according to the substitution, right? So we plug 1 in there, we get 2. Plug b in there, we get b squared plus 1. And then the integral becomes du over u. And then we know that that is a natural log. And so we get the natural log of u evaluated from 2 to b squared plus 1. Then we plug those in. We get limit as b goes to infinity of natural log of b squared plus 1 minus the natural log of 2. And then we just have to take that limit, and you can see that as b goes to infinity, well, we've got a b squared plus 1 and a natural log. If you plug in very large numbers for a natural log function, it just keeps getting bigger and bigger and bigger. So we know this thing is going to go to infinity. And if we remember back to what, improper integrals, when we were talking about that topic, if you get a limit of infinity, that means this thing diverges, right? So the function, or this integral diverges, and so according to the integral test tells us that the series must also diverge. Okay, and you can see that's what the conclusion of the integral test says. Basically, the integral and the series diverge or converge together. Now, let me just show you kind of quickly about maybe why this test actually works. Let me just consider the following. What if I was asking about, let's actually do this series here. What if I was asking about this particular series here? We're going to do this in a second here, but suppose I have this series, right, 1 over n, and I want to show that this thing converges or diverges, right? So using the integral test, this one's a pretty quick one. We can take the limit as b goes to infinity of integral from 1 to b, 1 over x dx, right? And so we know what that antiderivative is. That's just ln x, right? So we'll get limit as b goes to infinity of ln x, and then I'll plug in the b and the 1, and I'll actually end up with ln b minus ln 1 is 0, and then we know that that's infinity, right? So that tells us that that particular series diverges, okay? Now this series that we're looking at here is actually called a p series. If you see the convergence of p series there, you can see that what is the definition of a p series? It's 1 over n to the power of p. Well, what's p in this case? P is just 1. Okay, so this is a p series with p equal to 1. And you can see right there on part 2 that it says that type of this particular series will diverge, because it says if p is equal to 1, it diverges. And we just demonstrated why it diverges because of this integral test. Okay. Now, graphically speaking, you can kind of also see why this series does what it does. You can even see kind of why this particular integral test works. So let's consider the function f of x equals 1 over x starting at x equals 1. Okay, so 1 over x is the function that I'm looking at here if I graph it. If I started at 1, then the output is 1, and then what does it do after that? It just sort of decreases like that towards 0, right? That's the 1 over x graph. Now we've just shown, according to the improper integral that we just did, that this thing diverges, right? So that means that all of this area here under that curve all the way out to infinity, that is an infinite area, right? So now let's consider, what if I wanted to graphically look at that series also? So what about that? I'm going to go ahead and graph the series in blue, but you can hopefully follow what I'm talking about when I look at the series itself. Here's the series, right? What is the first term of that series? It's 1, right? Just if you plug in 1, you get 1 over 1. And so notice that you can actually graphically see that as well. If I draw this box here, you can see that the width is 1, right? And so if you look at this box right here that I've just drawn in blue, what is the area of that box? Well, isn't it just 1? I mean, the width is 1 and the height is also 1. 1 times 1 is 1, right? So the area of that box is actually the same as the first term of that series, right? 1. And what about the second term of the series? Second term of the series is 1/2, right? You can actually draw that box too, right? Because all of these have width 1, and so it's just going to be 1 times something, 1 times the height, really. Well, what's the height? The height is 1/2. And so this is the area that would represent the second term, right? 1 over 2. And if you add them together, the first box plus the second box, you're going to get the partial sum, second partial sum, right? And this just continues, right? You can visually represent all of the terms of this particular series by just drawing this particular box. So that one's going to have area 1/3 and 1/4 and so on. Right? You see, so these boxes that I'm drawing here actually visually represent the sum of the series. Right? 1 plus 1/2 plus 1/3 plus 1/4, etc., etc. Everybody see what I'm talking about there? The blue boxes are a visual representation of the sum of the series. And you can see that since that improper integral diverged, that means that there was infinite area under this curve, right? Infinite area under that curve. But you can also see that there's all this extra stuff from the series, right? And so clearly the sum of the series is actually larger than the sum of the total area of that improper integral, right? And so this sort of visually demonstrates that indeed this series, all those boxes, that's the sum of the series, right? But that's bigger than the total area under the curve, and we've already established that the area under the curve is infinite, so therefore the series has to also represent an infinite value. Okay, so that's kind of a visual representation about why this integral test actually works and does what it's supposed to do. These things called p-series, like I said, the only real benefit of this integral test, it's really the test of last resort. It's the last test you would ever want to use because it's kind of a lot of work. But it does establish these things that are called p-series, and that's very beneficial to us as well. So what is a p-series? You can see that is just any series that has this particular form. 1 over n raised to some power. That's a p-series. Okay, and you can see under what conditions this will converge or not. Okay, so just be clear, this is important because we're going to use p-series a lot. These converge. It says it on the paper, I'm going to write it anyway because it is important. This converges if p is greater than 1. Okay, strictly greater than 1. And it diverges if p is between 0 and 1, including 1. Okay, and excluding 0 wouldn't make any sense to have it at 0 anyway. I mean, it would just be a bunch of ones then though added together. So anyway, everybody clear on under conditions the p-series will converge. They're very series to test for convergence because all you have to do is just look at it to tell if it converges or not, right? If you can establish that you have yourself a p-series, you just need to decide what p is, and that will tell you whether the series converges or not. So very simple way to check a p-series for convergence. You just have to look at it. So let's take a look at that second. And again, the reason that these things do what they do, you saw we established why it diverges if p is equal to 1, right? We did that one. If p is equal to 1, that was the 1 over n series. But you can kind of see what happens if p is going to be bigger than 1. If p is bigger than 1, then what's going to happen to this integral right here? Because p is bigger than 1, so that was the second power there, right? Then what's going to happen to this integral? Like, what's the integral of 1 over x squared? Well, that's not the same thing, right? That's not use a natural log. That's the same as x to the minus 2, right? And you can kind of see that that antiderivative is 1 over x. Well, what's then that would become 1 over b, right? When you plug in the b there, I'm not going through all the work, but you can see that that's what you would be taking the limit for, right? That would be the last step. And since there's no natural log there and the b's are all in the denominator now, well, that's going to go to 0 and that is going to converge, right? And so the breaking point here is the point where that 1 over b turns into a natural log, and that occurs when that p-value is actually equal to 1. Anything bigger than that, you're going to get this situation where you've got the b's in the denominator and they're going to go to 0. Okay, so they'll converge in that case. All right, so let's do those two problems here in example 2. So again, it's very simple. Once you know what conditions there are for convergence for these p-series, like I said, you may have to do one little first step where you have to simplify it or something like that. But other than that, once you've established what that p-value is, then you're pretty much done. And so here I would say, well, that's a fractional. You should change that to a fractional exponent, and then you can see what the p is, right? This is a 1/3. So here p is equal to 1/3. And so we check, well, where's 1/3? 1/3 right there, right? And so this thing has to diverge. So you see how simple that is to tell for convergence of p-series. Just look at the number, that's it. For part B, similar. Again, you may have to do one little step at first, change it to a fractional exponent or something like that, and then just determine what that p-value is. So again, change roots to powers. Here you're going to get 2 over n to the, that's going to have to be a 3 halves power, right? 3 halves power. Well, again, just check, how does that compare? Well, 3 halves is certainly bigger than 1, right? And so that's all we need to know. This thing converges. Not too bad, huh? So p-series are very nice just because of this reason. Yeah, okay, so if you read through that bottom part there, just the last line there, I'm looking at the bottom of where it says remainder estimate for integral test. Just let's skip right to that last line there. It says these inequalities give a lower bound and an upper bound for S. They provide a more accurate approximation to the sum of the series than the partial sum Sn does. Okay, so what they're saying there is if you want to get, if you, for whatever reason, you want to find the sum of a series, or at least approximate the sum of a series, you can use this integral stuff here to do that. I'm not going to spend much time on this, and in fact, I think I deleted all these problems from the homework. But the point here is that if you want to approximate a power series, you can do it with these particular sums here, with these integrals, okay? Basically, that thing that they're saying there, where they put this, n plus 1 to infinity, when they say this, what is that Rn there? That Rn is the remainder, and you can see what it says right there, Rn is equal to S minus Sn. Okay, so what is S? S is the actual sum of the series. And what is Sn? Sn is the nth partial sum of the series. So what is the nth partial sum? Remember, the nth partial sum of a particular series is just if you, instead of going to infinity on the series, you just stop at some finite number, right? So suppose I have a series an, the 10th partial sum would be like S10, right? S10 is equal to this. I would stop at 10, okay? And then that would give me the first 10 terms of the series added together. Now remember that with convergent series, those terms that, you know, anything beyond, say, the 10th or 50th or whatever, some small finite number, they're going to be pretty tiny. Those terms that you're adding on, you know, after you pass the 10th or 50th or whatever term, they're going to be really small. And so oftentimes you get a really good approximation by just taking the first 10 terms of a series. That actually ends up really being really close to the actual sum of the series. Well, what this is telling us is that if you want to know how much of an error you have, this is Rn is sort of like the error term. How far away are you from the actual sum of the series? Well, it turns out that these integrals are telling you how far. If you want to know what the error is for, say, the 10th, then you would take the integral from 10 to infinity on that one, integral from 11 to infinity on that one. Those are all going to be really tiny values. So what we're going to find is that this Rn is going to be very small. And so you get a small error on what the actual sum of the series is. And then that middle, or that last line that they have there, actually tells you a way to find a very good approximation for the actual sum. You see that there's just the s in the middle there. And so you could take the nth partial sum and add it to that integral with the n plus 1 on the bottom. You could do the same thing on the other side with the n on the bottom. That difference is going to be extremely tiny, and so you can get a really good approximation for the actual sum of the series itself by using these inequalities right here. Anyway, like I said, that's not super important to us. Just know that if you want to actually use a series for some reason and you want to know what the sum of the series is, it's oftentimes best to just approximate it. And this is giving us a good method to approximate the sums. That's really all you need to take away from it, is what I was just saying there. And even the rest of this stuff, I'm actually just going to skip this too, because the integral test is really not that important for us. All we need to know as far as the integral test is concerned is that it generates these things that are called p-series for us, and it tells us very simply, does the series converge or not? Does this p-series converge or not? And that comes directly from the integral test. Yeah, in fact, I'll just share it right now so that you at least have the solutions for this, and then move on. So let me share Michael's work real quick so you at least have that, and then we'll go on to 11.4. So you can kind of see just on there what a pain it is in some of these problems to use the integral test, like b 1 over n squared plus 4. That's a trig substitution you have to do there, although you could actually use the formula for that one if you wanted to, the arctan formula. But yeah, that's a trig sub, and then yeah, you have to do all that stuff for just to determine whether or not it converges. it turns out it does. That one does. And then the part C, another one, just we'll find that there's much easier ways to tell if these things converge or not. So that's why I kind of don't really like the integral test, because you can see there's a lot of work, a lot of place to make mistakes.